What was the challenge for this competition? The challenge for this competition is to build a robot using the VEX EXP kit provided by the Imperial Valley MESA program to overcome the two challenges imposed in the competition, which is divided into the autonomous part, where the robot has to grab a ball and leave it in a determined area, and the teleoperated rounds, where the robot has to be able to get a ball from a human and then put it in a basket up a post.
While brainstorming ways to solve the teleoperated task from the challenge, we decided we would use a catapult or something similar to launch the ball, which we 3D printed and was powered by an electric motor that moved the arm. And for the autonomous part of the challenge, we needed something to move the ball, so we decided to use the basic claw robot design from the VEX EXP instructions, but modify it to suit our the things we needed to complete all the tasks. And I'll have pictures of both of those. The VEX robot is right here, and the catapult we used in our design is right here. For the human player device, we needed something to drop the ball into the catapult so that it could carry it. And we decided to use cardboard to create a dropper for the ball, so it would roll right down and land right into the catapult. And there's a picture of it right here.
So the first obstacle that we encountered was that the catapult just wasn't generating enough speed to launch the ball far enough. So the first thing we did was we replaced the metal pieces that were originally provided in the kit with a fully 3D printed model, which increased the motor's efficiency since it was now pushing less weight. We had also initially just created a little shelf to keep the catapult resting at a certain angle, which made loading the balls really easy. But we later realized that the more the gear spun, the faster and further the ball would go. So we got rid of that little shelf and we just created a code that would allow the catapult to rise to that same angle when loading the ball, but then return all the way down before launching for maximum power. Another issue was that when asked to drive straight, the robot would just start drifting to the right. So we also fixed this with the code. We just set a fixed position as drive heading 0 and then created a range so that every time the robot would drift outside of that range, it would correct itself and return to drive heading 0.
Our robot has 4 main abilities. The first one here is the claw, which is used to pick up the ball, transport it, as well as a distance sensor, which we use to make sure the ball reached the correct place, and the color sensor to make sure the robot could detect the color where the ball needed to be dropped. And then the robot also has a catapult, which is demonstrated here, to reach the net, as well as our human player device that we use to drop the ball inside.
It has started to be a viable idea to use robots in the chemical labs to constantly synthesize different materials with slightly different challenges each time. One example being the Andy Cooper's lab at the University of Liverpool, UK, where a robot equipped with sensors and an AI is capable of working with minor human supervision while rising efficiency. Another sector that is fairly in the daily life is the automotive industry, where robots are used in factories to increase efficiency and reduce costs at the moment of car production and assembly. An example of this will be the Toyota Motors factory in Kentucky, in Georgetown, Kentucky, where industrial robotic arms are used as part of the assembly line.
Lines 40 to 42 of the code establish the starting position of the robot at 0 degrees when the program is started.
So in lines 46 through 48, basically they set the catapult at an angle in which it is able to more easily grab the ball when we drop it into our device. It sets the RPM to 26, and after it does that, it spins it to a 45-degree angle. This is done by pressing the up button on the controller, and yeah.
In lines 52 to 55, we have set up the movement for our catapult. We first set this movement to be the controller button L1. Once L1 is pressed, we set the velocity to 650 RPM, whilst also changing the max torque to 200%. Line 55 makes the catapult spin to a specific degree measurement.
Lines 59 to 61 of the code are to return the catapult to its original resting position. When we press controller button L2, the velocity of the catapult is set to 12 rotations per minute. It then spins to its original position, which is 0 degrees.
In line 77 to 79, we set up the controller to open the robotic claw we have at the bottom. By this, the code says, if controller dot bottom A pressing, this meaning that if the bottom A is pressing, then claw set up its velocity to 30 revolutions per minute, and then claw dot spin to position 90 degrees with no weight. This meaning that the claw will set up its velocity to 30 revolutions per minute, and then change its position 90 degrees without waiting.